I hope everyone's having a great evening. I'm Mr. Ish. Thank you for joining me. In this video, we're talking about one of those topics which is usually an irritation for most students, pre-calculus students, that is conic rotation. We have over here in the very top a standard general equation form for all the conic sections you've looked at so far in terms of the pre-calculus, everything with regards to the hyperbolas, ellipses, the circles, the parabolas, everything on a regular x and y system, and you know that looks something like this, an x and y plane, and your depictions were on that. If supposedly there was a conic section which was rotated by a certain degree, we don't know what that degree was, but it was rotated, and then you had a new modified x and y plane. This became x prime and that became y prime. Originally we have x and y, and you can have a conic section that's rotated compared to what it was before. Then the general equation form changes and you see a new element pop in here, and that's this right here, the bxy term. This xy term indicates there's some sort of rotation at play. To eliminate this term, which is what usually is the goal for these types of questions, the example that you'll see, you have to do what is called a rotation of axis. When you do a rotation of axis, you're trying to change the axis to that what it would have been if supposedly everything were parallel to your conic rotation, to the axis of that conic rotation. When you're doing that, you're basically going to be generating a form of this equation with slightly modified, and that modified form will look something like this. And what will happen is this bxy term will be lost in the procedure, and it will be a good thing that it will be lost because you need it to go away. But you see how you have all of these primes come into the way? It shows that now everything has been adjusted accordingly by this rotation of axis procedure. To do this rotation of axis procedure, you basically have to understand a couple of equations. One is, how do you determine what this degree of rotation was? And there's a formula for that. Cotan 2 theta is equal to a minus c over b. But what exactly is this a, c, and b? These are what you're seeing here. This a over here, the c here, and the b here. They easily fall into that, and you solve for the theta, and that gives you the degree of rotation. Another thing you need in terms of the substitutions that which will come into play to help you generate this new equation form right here in the xy system is this: x and y will equal in terms of some substitutions. And what are these? It will be x is equal to x prime cosine theta minus y prime sine theta, and you got to remember this. Now for what the y will equal, you have another form which is x prime sine theta plus y prime cosine theta. And see how things are slightly different here. You have x is equal to x prime cosine theta minus y prime sine theta, but the y is equal to x prime sine theta plus y prime cosine theta. And these three equations right here, this one right here, and then these two right here, in terms of the substitutions, are what you need to help you achieve this rotation of axis. So let's look at one simplified example, and then we'll use that for the remainder of this video. So our question is this: we have to write this equation xy minus 1 equals 0 in the standard form. But before you do that, you want to identify what the various coefficients are, because you need those coefficients, and you can convert everything into this form. You have a 0x square, but you have a xy, and then you have a 0y square, and you have a 0x plus 0y plus f. But here the plus is really a minus, because we're seeing a minus 1 is equal to 0. What is the degree of rotation that's involved? Well, we have a wonderful equation. Cotangent 2 theta is equal to a minus c over b. I have an a over here, I have a c here, and I have a b. The b happens to be a coefficient, which is 1. Cotangent 2 theta is equal to 0 minus 0 over 1, which is equal to 0. If you were to solve for this, bringing in the arc cotangent or the inverse cotangent, you'd have 2 theta is equal to pi over 2, and then theta is equal to pi over 4. That tells you what you have in terms of the degree of rotation. Then you also have those two equations for the substitution. X is equal to and y is equal to, and you know what those equations are. I've written them before for you. X is equal to x prime cosine theta minus y prime sine theta, and then y is equal to x prime sine theta plus y prime cosine theta. In all instances here, the theta is pi over 4. Sine of pi over 4 or 45 degrees, cosine of pi over 4 or 45 degrees is always equal to 1 over root 2. All you have to do is bring that into play. When you bring that into play, in terms of these thetas over here, you'll have x prime over root 2 minus y prime over root 2, which you can consolidate as this x prime minus y prime over root 2, and this is equal to x. Now when you're looking at the y equation form, you know you're bringing in the root 2 over here in the denominator, because sine and cosine of 45 is always 1 over root 2. And you have this come out, x prime plus y prime over root 2, and this is equal to y. So we have this coming out, we have this coming out, but what do we do with it? You have this equation over here which you have to convert into the standard form. That right there is an equation in the xy system. It's here in the xy system, because this specific equation has a term which is xy. You have to get rid of that xy term, and when you get rid of it, you'll have converted into the x prime y prime system, which will then tell you exactly what you were dealing with. You have something here in the xy system because it has an xy term. When you get rid of this term by the process of rotation of axes, you will have converted into this x prime y prime system, and I'll tell you again what you have. And how can you get rid of it? By these substitutions. You have x is equal to this, you have y is equal to this, and you put them right over here. When you do xy, you put that in. You have a x prime minus y prime over root 2, and then you have a x prime plus y prime over root 2. All of this is equal to a 1. You have a conjugate over here being multiplied, a minus b times a plus b. You'll have no intermediate terms, so everything is easy. When you simplify this and you do this operation, you'll have x prime square over 2 minus y prime square over 2 is equal to 1. When you're looking at this, it clicks a bell as to what you're dealing with. You're dealing with something which looks like x square over a square minus y square over b square, which is basically, you know, a horizontally directed hyperbola. We have a over here, we have b over here, but these are a square and b square. But we can easily determine what a and b are. A is going to be root 2 and b is equal to root 2. So we're having all of this come into play. We've already determined now that we were dealing here all along with the hyperbola. That is going to be a rotated hyperbola. So let's figure out what we have here with regards to this x prime y prime system, and we can do all of that because now we need to determine what the vertices are. How can you determine the vertices? Well, you know you have a is equal to root 2. When a is equal to root 2, that's giving you vertices. It's plus and minus root 2 comma 0, which is really root 2 comma 0 and minus root 2 comma 0. These values, there are 4 of these values. There's an x, there's a y, there's an x and a y. You plug them individually in these. When you put them in here, you're getting 2 coordinate pairs. Look what I will be doing. I'll do root 2 comma 0 and I'll put it in here in the first equation. When I put root 2 comma 0, we can do it all mentally because zeros help us out quite a bit. You have a root 2 divided by root 2, you get a 1. Now when you put minus root 2 comma 0 into the same x equals equation, you have a minus root 2 divided by root 2, you get a minus 1. When you put this root 2 comma 0 in this equation, you have a root 2 over root 2, that gives you a y value of a 1. When you put this one right here, you put minus root 2 and a 0, you get a minus root 2 divided by root 2, that gives you a y value here of a minus 1. But you see how we've gotten a new set of coordinate pairs, 1 comma 1 and minus 1 comma minus 1. And then we also have these. One represents the vertices in one system, the other represents the vertices in the other system. But which system do they belong to? In the x prime y prime system, we will have these vertices. They will be right over here, minus root 2 comma 0 and root 2 comma 0. In the xy system, which is the equation we were starting out with, which had an xy in the equation, your vertices were 1 comma 1 and minus 1 comma minus 1, and that makes sense. And I'll tell you why it makes sense. Because when you did the procedure of rotation of axes, you eliminated this xy system. This equation here became this equation right over here, and let's highlight it a little better for you right here. It became this equation right here, and in this equation you're not seeing an xy term. In this system, your vertices of this hyperbola are minus root 2 comma 0 and root 2 comma 0. In the original xy system, which has the xy component, your hyperbolic vertex components are 1 comma 1 and minus 1 comma minus 1. And now it would make sense to actually graph this for you, and I need to make some space. I can make space by eliminating these formulas over here for you, because you know what they are and I don't need to show you those anymore. Let's show you here everything now in the x prime y prime system. X prime y prime system, you have something which rotated 45 degrees. I'm not writing 45, but we know it rotated 45 degrees. And you know we have something which looks like this. In this system, you have these in terms of vertices for a horizontally directed hyperbola, except it's horizontal on this new x-axis, which is your x prime axis. You have a positive root 2 comma 0, and you have a minus root 2 comma 0, and you have a hyperbola which looks something like this. And of course, if you wanted to be fancy, you could determine the asymptotes we want, but that would be your graph of this hyperbola in the x prime y prime system. In the xy system, if you were to do this entire graph, and we can graph it out for you now over here, I'll erase this part over here because we don't need it. In the regular xy system, you would have a hyperbola which would have the vertices here 1 comma 1 and minus 1, and you could see exactly what they are right here, and your graph would look something like this. But you can see how the axes here are the x and the y axis, and you see how the hyperbola is there. But here you have a x prime and a y prime set of axes, and your hyperbola looks like that. The equation of this hyperbola graph is xy minus 1, which you have. The equation of this is basically x prime whole square over 2 minus y prime whole square over 2. Now granted, I understand rotation of conics is a tricky subject because it is a lot to keep in mind as to what's going on and what systems are being involved, but this right here is the procedure that is involved. You see how the procedure starts with the rotation of axes. You have to eliminate the xy component, and your equation here in the standard form does not have the xy component. You've gone originally here from the xy system to the x prime y prime system, and in that procedure what we have done is we've rotated the axis. You see there's a rotation of the axis from here, we've rotated to over here. And that's all I wanted to show you for this specific video. Thank you for watching. Have a nice day.